is the morning talk for the day one, and so I thought I should comment a little bit on the general theme of the workshop before starting to comment on the coding Chern-Simons. And so one of the things you might have noticed is that this is a conference on three facets of R matrices, which is yeah. In fact, you're going to have a talk about three facets in the in the afternoon. But let's see. At least in the program, when we wrote the program, actually I didn't write the program, but proposal. But the other organizers kindly wrote a fantastic proposal for us, which is why we can be here. And when that happened, let's see. So there was three facets of R matrices, and so we have the R matrices. That's something very concrete. You can specify representations, and then there is a related integrable models, and etc. And then at the algebra level, there is a Yangians, and all that. So and quantum affine, elliptic algebras. So this is one concrete thing, and which is the unifying theme of this conference. So and then there are three different aspects to this R matrices which we have in mind. And so one is the geometric approach. So one might call the geometric approach. So this is I think what's going to be covered in the talk afternoon. So this is about for example stable envelopes and the things like that. Envelope and things like that. So if you for concrete paper, for example, that's what Morik and Okunko does, and the story about geometric representation theory. So we have some experts on that, and so that is the one geometric aspect. Now there is also analytic aspect. What analytic aspects. And so that's what Sachin and Curtis and others have worked on. And so I let some other people comment more on that. So this is yeah. So indeed, for example, that is by people by Sachin, also Aurelio, and also with Curtis and others. So there is an analytic approach to this R matrix, and then the other one is the gauge theory approach, gauge theoretic. Yeah, so this is what I'm going to describe and what was described in the previous talk, coding Chern-Simons and other things. And so this is yet another approach initiated by Costello, and also in my paper with the Edwin Costello. So okay, so these are several different approaches to how to understand integrability and R matrices in Yangians. So one of the aims of this program is to try to bring together expertise from different aspects and see what will happen. So you never know what's going to happen, and I don't think we are going to write a paper this week, but the hope is that something interesting, something new will be created out of this. So that's the whole point. So please do try to ask questions, etc. Or if you have something in mind which you might want to know about other. For example, suppose that you might work on one of them, and you have some other things you want to know about other things, and then you should ask the experts, and you should get them asked and ask questions. Or so you might first hear it in different ways. So you can try to understand the relations between different approaches. Something is known here. What about here? And the things like that. So that's what we might hope to achieve. At least one of the things we might hope to achieve this week. So please have that in mind. And yeah, so for me, let's see, I myself have been working on the gauge heuristic side for the moment. But there's I'm also working on some related to this geometric approach a little bit, at least some aspects of that. And this analytic approach is less obvious to me, so I'd be very eager to learn. So so then okay, so this for the Chern-Simons story, this is the thing I'm going to describe in the rest of my talk. And well, one of the interesting things about this is that this is related to a lot of, well, of course, other things I'm sure too, but to a lot of other structures. In particular, it's part of this string theory saga. So it's part of the gigantic structure, string theory and supersymmetric gauge theory. And so that contains a lot of mathematics. So the whole, everything you do in this approach, it has a counterpart avatars in string theory various aspects. So a lot of discussions about string dualities, etc. do up, right? And that has some should have some mathematical implications or the other way around. So okay, so that is the very broad viewpoint on what we might want to achieve in this week. And let me come to 4D Chern-Simons. So okay, so 4D Chern-Simons, what is that? Well, okay, so there was already an explanation, so I don't have to reintroduce it. And but let's see. So the one aspect of 4D Chern-Simons I want to emphasize is that it's closely related with the 3D-dimensional Chern-Simons theory. So in fact, the discussion goes quite similar, and there are a lot of parallels. So if you know whatever is discussed for 3D Chern-Simons and representation theories associated with that, there could be some natural 4D Chern-Simons counterpart of that. And if you have started with the 3D Chern-Simons, then there was an explanation of the knot invariance. And the 3-manifold invariance. And this is due with the quantum groups. And so these are related aspects. And and this was a very topic. And what is happening for the level of the 4D Chern-Simons is somewhat similar. So we have for 4D Chern-Simons. And here, let's see, for example, I might put integral models here. So there is an R matrix and things like that. And then there is a underlying algebra, which is here, which I might write Yangian and other algebras. So there is again a relation in between. And in fact, the story is very parallel. So in fact, the question of whether we can identify this theory was there already in the at least the early 90s or even late 80s or so when Witten was working on this 3D Chern-Simons theory. And certainly there are a lot of discussions about relating knot invariants and integral models. And of course, when Jones worked out the knot invariants, it was partly motivated by insights from integral models. And so certainly there was a lot of interactions between here and there in various different occasions. And so that's not at all a secret. And so so it was an obvious question for Witten tried to ask what there could be a counterpart, integral model counterpart for the 3D Chern-Simons theory. But that one it turns out to be a very simple answer, and that's the 4D Chern-Simons which we are talking about. So and this makes things clear that you can ask similar questions, and so that might be the one way to see. Well, of course, the one difference there are differences between these stories. So it's not like you can copy everything. It's useful to think about whether we can do something similar for this case compared with this case. So it's very useful. But on the other hand, you cannot always copy everything, and there are important differences. And of course, that's the difference between integral models and knots. They're very different subjects, and so there are differences and similarities. And so one aspect of difference, which is important here, is that okay, so it's 4D Chern-Simons is some quantum field theory, but in practice, how to analyze these theories tends to be different between two different theories. First of all, so as was already commented, so this is a topological quantum field theory. 3D Chern-Simons is a topological quantum field theory, but this is like a mixture. So 4D is divided 2D and 2D, and so in the 2D direction, this is the TQFT. So if you like, this is where the E2 algebra lives, so this is like more like a holomorphic theory. Holomorphic. So this is where this VOA lives. So this theory is a mixture of a topological holomorphic theory. So and certainly it's not in general not the topological quantum field theory. It depends on the complex structure here. So that means that the typical way of discussing 3D TQFT does not apply, at least naively. So if you have a 3D TQFT, okay, so you can start with the Chern-Simons action and the path integral, but one way to understand it instead is that there is a modular tensor category, for example, et cetera, et cetera. So, and of course, we have the single type definition, et cetera. So that's one way to approach the question of TQFT. But that is, okay, so there is generalization in a sense of by factorization algebra, et cetera, but that itself, that original TQFT discussion in itself doesn't apply. And some of the negatives that the approach to this 4D Chern-Simons theory taken so far is to analyze this model using some perturbative expansion. So this is a 4D quantum field theory. And okay, so quantum field theory, so there is H bar expansion. And what we're going to do here is to do the perturbative expansion. In this parameter, in this H bar, this is a Planck constant in the quantum field theory, but it's also the deformation parameter of the Yangian. So this is the deformation parameter of the Yangian. So this H bar, for example, this is a Yangian, and when this H bar goes to 0, it simply becomes the universal embedding algebra with the formal variable, which is a spectral parameter. So there is this deformation parameter, and so there is a deformation parameter which we sometimes drop, but if you read the original Greenfield article, it's actually there already. So there is an H bar parameter. He was writing H, but anyway, so there is a deformation parameter, and the deformation planes do appear in quantum field theory. And what we're going to do is to do the analysis order by order in H bar. At least that's the first type of thing you do in 4D Chern-Simons theory. So concretely, okay, I'm coming to that afterwards, but concretely, what I'm going to do is that, for example, R matrix, Z, with respect to some representation. So this is R matrix, and this depends on the H bar parameter. And then this has an expansion, starting with the identity plus H bar plus classical R matrix, and H bar squared plus some other stuff, etc. So there is this H bar expansion. And so in particular, in this discussion, we are looking at the R matrix, which has this leading piece, identity plus corrections. So that's what people call the quasi-classical R matrix. And then this piece, leading piece, is the classical R matrix, but R for small r, classical small r matrix. So semi-classical R matrix, and there are corrections. And as you probably know, so actually, if you know this, that's already highly constrained, because essentially this one obeys the Yang-Baxter equation. So if you know this, you can do the sub-recursively, essentially solve for higher things. So so that's the argument that you have to make it a little bit more precise, but if you know this piece, that's determines the structure, assuming that this satisfies the Yang-Baxter equation. And but the point is that instead of getting this on the nose, at least so far, what has been done so far in the 4D amuse is mostly about computing this order by order. If you like, you can compute this and that, and that there is a technique for doing that. That's the prime analysis, the prime method for analysis for the 4D Chern-Simons. And then well, okay, so that is the canonical method to analyze 4D Chern-Simons. That's a big difference from 3D Chern-Simons. Except that, well, there is still a counterpart in 3D Chern-Simons. So maybe that's what I might want to emphasize at least here. So, okay, 3D Chern-Simons theory, it's a topological quantum field theory. So people usually use other methods to analyze that, using Sargeri formula. That's how Reshidik Interai, for example, obtained the three-manifold invariant. But let's see, but if 3D Chern-Simons is a quantum field theory, so just like a 4D Chern-Simons, you can still do perturbative expansion. And certainly people have done that. So perturbative expansion, you can do that. Okay, so here, even here, you can do the perturbative expansion. And so that's associated with the name of the, for example, Vasiliev and also Kontsevich, more universally, and other people. So well, or there are earlier papers, but anyway. So so there is you can do perturbative Chern-Simons theory, and then there the discussion is somewhat similar. So in other words, there is still H bar parameter here, H bar parameter, and you do the expansion, and then you're going to have some combinatorial sum at order H bar. And that was formulated in the language of chord diagrams, etc. And the discussion here is we're going to see structures which is very similar to what we find here. So what we're going to do now is very similar to what people do in the usual 3D perturbative Chern-Simons theory. And that's why and that itself is an interesting subject that defines a finite type invariant, for example. And yeah, and of course, in this case, that was related because if you have perturbative expansion of the Chern-Simons theory, that is one aspect of how to formulate the WRT invariant, and that gives order by order corrections. And but quite often you can actually sum it up to a well-defined series. So that is a perturbative expansion. It's actually divergent usually, divergent series, but you can sum it up, and then you can obtain the full answer, which is the WRT invariant. So so that is the point of summing up the perturbative expansion. So this in general quantum field theory, it's hard to define non-perturbatively. So when people, in fact, physicists claim that they know what the quantum field theory is, typically they know how to compute the perturbative expansion, which is a divergent series. But when you sum it up, you have a well-defined answer, which we call the non-perturbative answer, and then you should get something. And if you want to know the full dependence, full R matrix, etc., that's the procedure you might want to do. So there is an aspect of non-perturbative things which is interesting in itself. But in the rest of my talk, I'm going to restrict to perturbative analysis. And but that itself is actually already interesting, and partly because the result itself is surprising. So if you know the R matrix, I think most of you, probably all of you know some R matrices, and you already know the answer. So yeah, you can expand, you get something. So it's not surprising that you can get all the answers. But if you're a physicist, actually, it's actually really surprising because if you open a quantum field theory textbook, and then typically there are some diagrams, and if you ask, okay, so your student might be asked to do this term, compute something like this term or this term in the quantum field theory textbook. If you go one higher order terms, it's very complicated, and maybe once in your life you do it, it's fine. Or maybe you write a program, and then all higher order terms, it's a mess. So you really have to be an expert and write a computer program for that, and etc. etc. And then after you get an answer, you get something. So it's extremely hard usually to compute this full series. That's a fact of life. So yeah, so that's you really need a very dedicated effort usually to compute all the higher order terms. But in this particular case, it is actually possible to compute this essentially all order because you already know the R matrix. So the fact that you can determine this all order H bar, if you're from representation sorry, oh, okay, it's nothing, you're expanding, yes. But from physics viewpoint, it's actually a rather surprising statement. And there are other cases, for example, if you have some supersymmetry, etc. Here you have some symmetry, which is Yangian, so which is essentially the reason why it works so well. But anyway, so there is also somewhat. So that's actually an example where something you might think kind of as a trivial, but might turn out to be extremely surprising, seen from for people coming from other backgrounds. So okay, so this is how the story goes. And now the question is so let me try to explain how the perturbative quantum computation works in somewhat more detail. And yeah, I apologize if you already know the basic quantum field theory, and then this what I'm going to say is kind of trivial. But this is a very broad audience, and I want to I thought that I should try to motivate more what I mean by doing this perturbative expansion. So like a technique like a Feynman diagram. And yeah, and then if you open the quantum field theory textbook, there are canonical ways of explaining that using there is a theory called the 5-4 theory, there's a Wick theorem, etc. So of course, one way to kind of repeat everything, but then you might get bored because some people already have heard it 100 times, and for other people it might be a little bit technical. So what I'm going to do is to try to do slightly differently. And by starting with here in this case, 3D Chern-Simons. And so I'm going to explain some aspects of perturbative expansion in 3D Chern-Simons. And then goes on, this one is not too different, it's similar. So so that's how I'm going to explain this structure. Any questions so far? Okay, yeah, okay. Then let's come to this blackboard and start discussing the Pythagorean expansion. So so I want to do a Pythagorean expansion of quantum field theory. So Feynman diagram. Okay, so maybe Pythagorean expansion. And in the 3D Chern-Simons series. Now, 3D Chern-Simons theory itself is already kind of complicated theory to explain the basic idea. So what usually physicists do is to try to simplify it. And the way I simplify it is let's go to the abelian gauge group. So gauge group is U1. So it's very simple. And then the action is simply action is simply 1 over h bar. This action is A H dA over the 3 manifold. So let's call it M3. So this is the Pythagorean expansion. Oh, sorry, not sorry. This is the Lagrangian action of the 3D Chern-Simons theory abelian. So there is a cubic term which we are going to come to afterwards. But this is the so far the action, and this A is the one form. And then there's obviously a gauge transformation. So A goes to A plus d lambda. So if it's the exact form, and then this action is invariant, so that's known as the gauge transformation. Okay, sorry, this is very easy. And okay, but now, okay, so then what we want to do is to try to compute the things from this action, and that is involves doing the path integral. So okay, so this A is the gauge field, and so okay, so this is the Lagrangian. So it's a function now of this one form field, and so this is the exponential of well, okay, depends on whether Euclidean or not. There is I, etc. But let's say. So let's do this, and this is the infamous path integral. This is a very complicated integral. So if you try to formulate this, most of the path giving the dominant contribution is like a highly non-differentiable, etc. So it's crazy function. It's actually very hard to imagine, but nevertheless, so even the physicists don't at least most of the physicists don't ever understand what is actually happening. But at least they know what. Yes. Oh yeah. Okay. I see. Maybe I should hear. Yeah. Great. So yeah, that's right. Okay, great. So yeah, if you come there again, please let me know. So yeah, that's right. So okay, so this is the partition function, and okay, so in the case of Chern-Simons theory, this is can give rise to interesting 3-manifold invariants, etc. But okay, but then in order to discuss something similar to us, it's you rather talk about the operators. So for example, you insert this A connection one form at some point. Okay, so this A, I wrote A, but A actually depends on the X, where X is the point and in the 3-manifold. So if you like, this is a map from 3-manifold, etc. But and then I want to compute something called a correlation function. Okay, so this means that take an expectation value, and this is to evaluate this integral over exponential of A, but with these two things inserted.
So the variable for this integral is A.
Sorry?
The variable for this integral is A.
Yes, A. Yes.
Okay.
Yes. So this is like this itself is A itself is like it depends on the point in the So it's it's an element of the map from it. Yeah, so it's 3-manifold. But but this itself is that's the thing you integrate all over. Yes. And so once you specify this, of course, these values are determined because it's a particular value for this whole field. So this itself is defined in the whole 3-manifold, and you take a particular point.
You get X and Y. And you
Yes, that's right. That's right. So if you like, you can. There is an evaluation map at 2 points, and then that's the thing inside. Yes. So yeah, that's right. So I sometimes write AX, but in fact, this is confusing. This X is a particular point, but this itself is defined in the whole 3-manifold. Yes, but at least that's the idea. Whatever this, and of course, it's not easy to define what it is, but at least that's the idea. Oh, how? And so that's the 2-point. That people sometimes call it the 2-point function, etc. So there is something happening here. So basically, idea is that something is happening. You specify that something should happen at point X. And something should have also at point Y, and then how are you going to fit in the middle? So that's the things you want to compute, and that's known as the correlation function. And of course it's okay, it's of course difficult to define this. If you're a mathematician, then you don't know what it is, but at least you're going to get some answer, which physicists claim to have justified, and that answer itself is something well defined mathematically. So you can just take it as this is just you can take it if you like as an inspiration, and whatever comes out as the actual thing. So that's certainly okay. But this you're writing that makes some things a little bit clearer. Now, okay, so what is this? So that's the question. And okay, so what is that? So well, it's the point is that here A, if you look at it itself, is depends on the point in the M3, etc. But anyway, A is a quadratic. So sorry, the action ADA. So this is something acting on A. So it's a quadratic, and this is also quadratics. So that's what people usually call the Gaussian integral. So that's something you can evaluate at least when you talk about the finite dimensional counterpart. So the finite dimensional counterpart, So finite dimensional counterpart. So finite dimensional counterpart is the force. So okay, so S to be, so let's consider vector. For example, vectors to be, okay, maybe like the ball B to be some vector 1 to D dimensions, for example. So D is a finite number. And then there is a action, which we might call something like action, which depends on this, and then this is a quadratic. So BA, QAB, BB, and the sum over AB, 1 to D. Okay, maybe I like make it IJ so that because I'm going to use it. Okay, it's just the index, it doesn't matter. But yeah, and then you can write a similar version to that, which is that you take BI, BJ. Okay, so then you take 1 over Z, and this is the integral of D from minus infinity to infinity, and then there's a BI, BJ exponential SD, etc. Okay, I'm not worried about factor of I, etc. And then this itself is the same one without this insertion, normalization factor. Okay, maybe I can write it just in case, but so this itself is like an integral B exponential ISB. Okay, and then the simple fact is that, okay, so then this is a linear algebra, you can evaluate it, and probably some of you are even teaching linear algebra courses, etc. So, and the answer is very simple. So it's basically, it's just the Q inverse IJ. So, okay, so I assume that this QIJ is invertible. And in fact, otherwise there's a flat direction, so the integral is not convergent. So, so that is the answer. So this is the finite dimensional counterpart. So you just take whatever operator acting on the quadratic piece and take an inverse. So that's what you get. And the idea is that you do exactly the same thing for this infinite dimensional case. And then it's not too difficult to imagine what happens. Because then you're going to have the okay, so this thing is going to be the basically like an operator. Okay, so there is a D which the operator, and so there is an operator D exterior derivatives. So you should have the inverse, something like an inverse, and evaluate at point Y. Just like there was an inverse of the matrix. And then what this means is that this is the Green's function propagator. But this is sometimes called a propagator. And this object is the object satisfying the equation that so this depends on the only on the difference. First of all, it depends only on the difference. And so it's inverse. So if you take it, if you apply the differential, and then you get the distribution located at the x equals to y. So I like this. This is highlighted as a 3 form. This is a 2 form. This is the 1 form derivative. So and then there is a it's actually undergrad physics problem to write it down. And then I think if I'm not wrong, and then this one has a form like 1 over 4 pi. And oh sorry, I'm getting a little bit small. But then I think there is a epsilon ijk. Let's see. Oh, okay, so that depends on the dimensions, but we are now in 3 dimensions. Oh, sorry. Okay, I'm looking for that. Right here, z equals to 1 over 4 pi. Okay, so that's z of x. So this has we are 3 dimensions, so it has 3 components, x, but this has 3 components, x1, x2, x3, and then these x1, dx2, dx3 plus cyclic. And then there is this length, x1 plus square plus, okay, maybe I can just like this, to the cubic power, something like this. Yeah, so this is a cubic power because it's space-time is 3 dimensions, and then there's this factor. So it's a propagator 2 form. And I write this because I'm going to get come to very similar things. So, okay, so then this is just the propagator 2 form. And now you already know what this is. For the first integral. So so that means that ax, ay. So this is a propagator 2 form, and that's written there. So this is the object. And well, okay, so this is known as observable, etc. Except that there is one subtlety in 3D Chern-Simons theory that this is not gauge invariant. So there is a gauge invariance which sends A to A plus B lambda, for example. And this thing is not gauge invariant, so you have to go to the gauge invariant object. And one way to do that is to consider the integral over some cycle, cross cycle of this A. So if you like, I can write dx and over x. And also yet another thing, dy over another cycle. So if C and C primes are closed paths, if they are closed paths, then you can do the gauge transformation. But this is if you do Stokes theorem, it's 0. So it's a gauge invariant object. So if you take a path, if you like a knot, and then this is a gauge invariant object, then you can talk about the 2-point functions. And then what you get is that integral of the dx dy over C and C prime of this propagator. And then this is known as the famous linking number of C and C prime. So what is happening here is that you take C and maybe C and C prime are might be linked indeed. And what this says is that, okay, let's take some point, for example, let's take here point X and another point Y. And then we have something called a propagator, which runs in between here, and then do the integral over this all the possible position x and y's. And so that is the object you are supposed to compute, and by doing that you get the linking number. And in fact, I think this itself is essentially known to Gauss because actually Gauss defines it. And this, I'm talking about the 3D Chern-Simons, but essentially the same problem appears in electromagnetism actually. So because we talk about flat connections, but the similar equation exists for magnetic fields actually. So I think exactly the same thing is kind of known to Gauss more or less, I think. But anyway, but the point is that here, but this has an intuitive appeal. So okay, so we are talking about 2-point functions, etc. Okay, so we have the etc. And then what is happening is that here, it's something. Okay, so it specifies that something should happen. So it emits a particle here and it's absorbed here or something like that. And then there are possible positions you can think about, and for that you have to integrate that out. So that is how you get this invariant, and this itself is an interesting topological invariance. So, and this is for abelian Chern-Simons theory. Now I have a little bit of time to come to generalize that first to no-abelian Chern-Simons theory. And where is it? Yeah, so no-abelian Chern-Simons theory, and then I come to 4D Chern-Simons theory.
So can I ask a question?
Yes, sure.
Linking number, it's a complex number, but do you know if it's like maybe a real number in some cases or?
Well, linking number is saying this itself is an integer in general.
Yeah.
Yes, so it basically counts how many times it links. Yes.
Okay.
So that itself is a non-trivial fact, which is not completely obvious from this definition, but yes. And yeah, but I mentioned this because I don't know. This is a simple example where I hope it's extremely obvious. But also it's also, if you're a geometer, probably you're supposed to know about some of these definitions, etc. And then that itself actually has a Feynman diagram interpretation. And actually what I'm going to do is very similar to this. in a slightly different setup. And the point is that here, I didn't really use the fact that the theory is topological, etc. I didn't use technical, topological quantum field theory as a map from Boltzmann category to something, etc. But just forget about all that and just do some integral. So that's actually how things go. And then that type of approach is not necessarily the most popular in mathematics, but it's actually useful in the sense that it works basically for almost any quantum field theory. But okay, that's a little bit overstatement, but at least almost any quantum field theory with Lagrangian description, weak coupling, etc. There are certain asterisks, but then this type of method works, and whether you can compute is a different issue. But so there is some universality here in there. So yeah, so now indeed the question is that so that has been around it, but that's related to the difficult question of how to formulate quantum field theory, etc., which I think at the part of level I think is achieved by Kevin and others. And so that itself can play a role at the more concrete level in this discussion. So let's come to yeah. So first the Noah-Abelian case, because we are still in the was what 19th century, 18th, no, maybe 18th century or something. So we should come to yeah. So okay. So what about the Noah-Abelian case? And in the Noah-Abelian case, it's okay. So what about general G? Okay, so general G, but I have in mind semi-simple G, etc. I think so. But as far as that is concerned, it doesn't matter whether it's SUN or SUN, etc. And so this is a real algebra, and I take the set of generators TA. So A1 to dimension of G, and then write on the explicit commutation relations that a commutator equals to what people call structure constant TC and sum over C. So so there is some description, and so in fact some aspect you can do universally without explicitly picking up the real algebra, etc. So that's of course how related to how concept itself defined, and that simulation should be applicable, and that's related to the question of how to realize the universal R matrix in the 4D Chern-Simons, etc. So you might have that in mind. But let's see. Okay, for general G, what is the difference? So the only difference is that whenever you write on the propagator, okay, so this itself is now real algebra valued. So you can write the one form as a combination of TA. Okay, so you don't have to do that. Maybe you can do it more abstractly, but one way is to expand everything in terms of generators. So now you have this index dependence, AB, and so the propagator now depends on a pair of indices for each generator of the real algebra. That's one difference. But another difference is that, okay, the Chern-Simons action. So, okay, so then this one becomes the generator. Now the propagator, what I was calling the propagator also has indices A and B. But in practice, if you take the action to be, if you choose the Killing nice generators, normalizing the Killing form, you can extract the indices together. Now, so another aspect is that 3D Chern-Simons action now contains the cubic terms. Maybe I can write it a little more precisely. AHA. So this is the invariant pairing. So okay, I think Brian was writing AH. This anyway, it's the same thing. And so there is a cubic term at least over the 3 manifold. So cubic term. So the cubic term, the fact that there is a cubic term means that there is a vertex, trivalent vertex. Where 3 lines come in, and then there is a structure constant, this FVC here. So that means that if the particle comes in, it can split out, or the particles and merge together. So there is a structure constant you can write down, F, and that's a difference. But the idea is not too different. For example, if you just have a diagram like this, previously you were talking about these lines, and in fact you can also do more lines, etc. But now we have first of all, we have the indices. Okay, so if you keep using this, the index doesn't change, but there might be other diagrams, like for example, this splits, and then ends, and maybe splits again, and things like that. So there are all these type of diagrams which appears. So this is the difference in the Noah-Abelian case. And of course, if you do this, you should sum up these diagrams, and you get more interesting invariant of 3 manifolds, which is this finite type invariance, part of the expansion of the WT-RT invariant. So these are the typical diagrams and how you compute it. So that is the idea of how to do computations in the non-abelian Chern-Simons theory. Any questions so far? Okay, yeah. Now let me come to the. Okay, I'm going through, but let me come to the actual stuff of the Yangians and 4D Chern-Simons theory, and it's not too different from this discussion, and so it's a little bit of detail differences. Yes.
So this green function is different now, right? Because
yes, green function is different. Yes. Yes, for example,
the same one, but you
have to change it. Yes, okay. That's right. For example, there was a power 3 somewhere, and that was related to space-time dimension 3. So if you go to 4 manifold, in fact, you're going to have power 4, for example. Yeah, so that's right. So the electromagnetism behavior changes, for example, in 1D, 2D, 3D. That's an interesting problem to think about in electromagnetic class. So indeed, these things are very different in different dimensions. But at least the structure is similar. So you always take green function, write down the action, and then look at the quadratic piece, and then take an inverse, and that's how you define the propagator, and use that as ingredient to do this computation. Yes. So perhaps I should emphasize again that at least so the path integral part is of course black box, but in a sense, whatever coming out with the resulting things, you can just formulate. So generate some diagrams like this, and for each diagram there is associated contributions and sum it up, etc. So you can define these things without any problem. Well, of course, here there is issue of gauge invariance, etc. So if you want to do it more systematically, you have to use the Batary-Minkowski formalism and the this cogent complex argument and things like that. So that's where the fun comes in. But at least, if you want to take a down to earth approach, then that's it. And in fact, I forgot to say that, for example, in this there is a gauge choice involved. Even in this example, there is a gauge choice involved in this choice of propagator. So for example, here I have this, but this is a 2 form, but this itself, for example, has ambiguity. So plus dg prime or something. So of course, this squared is 0, so you can just add something, and then it still satisfies this thing, right? So there's actually a huge degeneracy, the choice, ambiguity in the choice of this g. But the point is that there is a the gauge statement of the gauge invariance is that you don't have to choose particular g, and then whatever choice you have, the answer is invariant. So sometimes so this one I actually took a canonical one, and I think if I'm correctly, this one is a star, Hodge star. You apply Hodge star, and then d equal to 0. So you take some particular one satisfying this condition, and that is known as the gauge fixing condition. And I'm going to that's the gauge fixed version of this one choice of the propagator. I'm going to use a similar choice in the 4D Chern-Simons discussion.
It's for the flat metric.
Yes, for the flat metric. Yes, that's right. So indeed, you have to, yes. Okay, so I guess I spent too much time on the 3D Chern-Simons, so let me come to 4D Chern-Simons. Yeah, so I think what Kontsevich and Vasiliev does should be essentially the same as the doing this Pythagorean expansion for Chern-Simons theory. Although it's actually the precise relation I actually don't know. So they have the formulations already, yeah. So it's not like you have to if you want to define something mathematically, you don't necessarily have to follow everything on the node. Sometimes you can take some relevant parts, and maybe that's enough. So, but at least I think it's clear that even Kontsevich, I think some of the ideas come from this Pythagorean Chern-Simons description. So, in similar spirit, we have the 4D Chern-Simons description, which I think is quite useful. And I think there are rooms for doing something similar. So maybe the next Kontsevich might be out from this one of the rooms. So I don't know. But anyway, so okay, so what is the 4D Chern-Simons computation? So 4D Chern-Simons computation is very similar. And okay, so 4D Chern-Simons. Okay, so what type of things we want to compute? Let's see. Okay, so gauge group G, and And let's see. So the object we are going to compute is the R matrix. Something, so graphically, it's something like this. And okay, so we need to first explain this picture. First, here we have this okay, so there is a spectral curve. I think he was writing X, I guess, and this is like M2. And so this is where the spectral parameter lives. Or in other words, so we need a complex structure on this manifold. And yeah, I might like to see spectral curve. And then, so this is where the complex structure lives. So these things are holomorphic here, and things are topological here. And here we have this one-dimensional object in the horizontal vertical direction. You can actually tilt it, and then there is a, but at least, and then what is this? So this itself is just like in the case of 3D Chern-Simons. It's essentially integral of the gauge field along this. There is a path gamma 1, gamma 2, and integral of the gauge field one form along the path. And well, except now it's no abelian, so you have to be careful with the ordering, etc. Physics is not the path order, but it's like a monodromy. And so this is defines the Wilson line operator associated with this path. So this is just like in the previous case, there was a link, and you integrate over the gauge field along the link. And I do exactly the same thing, but now this path is taken along one of the topological directions. Yeah, so in fact, these projections, we actually don't see the up or below. So, and then they are located at different points. So you have points Z and Z prime, and okay, so these are different points. So these are the one-dimensional lines, and along each lines, you integrate the gauge field along the line. And then we are interested in computing the correlation functions of these two operators. So that's how you get the R matrix. And in general, you can, okay, here we just have two R matrices, but you can have a line of defects, etc. And that's exactly how you make an integral lattice. So you have many parallel lines, and that's how you realize the lattice as in integrable lattice models. But here I'm now zooming on to this particular intersection between two lines. And that's where something should happen, it's supposed to happen. And that's the point where R matrix should come out. And okay, so look, but then okay, so the question is how to do the computations, and the computation should be similar. So computation should be similar, and in fact, graphically, it should be very similar to the previous case. So namely, for example, in one of the leading terms, the simplest diagrams you can write down is like this. So, well, previously I was writing this, for example, there are two rings, and then the linking number is given by having this propagator and integrating. So it's somewhat similar to this diagram. So if you like, you can think of this as a part of this circle, but now stretched along a line, and it's a similar line, and you use exactly the same similar things. But of course things are different. It's not completely topological. There is a holomorphic dependence, and somewhat related this line is confined to this topological frame. It doesn't go into this direction. And yeah, so this is the leading diagram. Of course, there are some corrections. For example, you can take two lines here, for example, or there are this, you can do more. There was a three trivalent vertex as the one, so you can obtain more corrections, etc. But at least there is a organization, and the result is a Pythagorean expansion. Okay, so Pythagorean expansion for the Chern-Simons theory. And here, instead of the linking numbers and things like that, we get the R matrix. So the full R matrix, as I was advertising, should be given by this expression. And this has an expansion like a starting from identity plus H bar times classical R matrix plus H bar squared, etc. So this is the structure I was advocating. And then this comes in because, okay, so you have two lines. They actually don't touch with each other. So let me write like this, just to emphasize that. And first, something might happen here. And so first possibility is nothing happens. So this is identity. And the second possibility is that something simplest happens. So in this case, there is a single thing branching off. And here, there is a subreading corrections. There is a diagram like this, for example. And so this is the order h bar to 0. This is order h bar, and this is order h bar to squared. And a good way to memorize that is that there is a loop. Here in this case, there is a loop running in the middle, and whenever there is a loop, you get the higher power of h bar. And this is the only diagram. In fact, you might worry that there might be other diagrams. For example, you can have the diagram like this, but you can verify that these diagrams actually, for symmetry reasons, they actually cancel. So some diagrams actually cancel. But anyway, at the leading order, here is only this diagram. So that's the diagram we want to evaluate.
And the diagram you drew there on the left board.
Sorry, yeah. In fact, this one, yeah. For example, this one, I think it's more like I think it's like a two loop, the h bar, the order h bar squared or something. Yeah.
And the one with the two in the right upper quadrant.
This one.
The two zigzag lines.
Yeah, there are two zigzag lines. So I think this itself. Okay, I don't remember, but probably this. Yeah, maybe this itself doesn't vanish. I don't remember. Maybe it vanishes. No, but I think it's okay actually. Yeah. Okay, maybe it vanishes. I need to. Yeah. I don't want to bet. Yeah. In any case, it's a high order contribution. So yeah. So in fact, the number of diagrams typically grows factorially. That's the reason why the part-double expansion is the asymptotic expansion in general. So it's a mess in general. And also because of the gauge, there is in quantum field theory you have to do the renormalization, etc. So sometimes you have to eliminate this term. So you need a homological argument to argue for that. And so that's a complication. But in the first order, the leading order, and this is the only diagram. Simplest diagram you can ever think of, and there's a single diagram. So we are very lucky that you just evaluate it. That's it.
So this formula is for the first order, or is it from?
Sorry, which formula?
So this formula you wrote for the R matrix elements here. W gamma 1, W gamma 2.
Sorry, which formula? Okay, I don't have formula here. Sorry.
This term W gamma 1, W gamma 2.
Yes.
Yeah.
Yes. Yeah, indeed. So this one gives the R matrix indeed. So
at the first order, or is it also valid for the?
Okay. So this one, yeah. So to all orders in H bar. Yes.
All orders.
Yes. So in fact, this is located at Z1, Z2. Yeah. In fact, I should write down some formulas. So, and then this is H bar. And okay, so first, and also I forgot to say that, of course, Wilson lines, you have to specify which representations you are in. So in fact, I have to take, so I have to evaluate it. This itself is a gauge, a joint body. So you have to evaluate this some representation. So there is a representation dependence, V1, V2, for example, and there is associated R matrix for that representation. Yes. And to all orders in H bar, yes.
So what are the role of V1 and V2? It's
sorry, no, V times V2. Yeah. Sorry.
What are the role of V1 and V2 in this picture?
Order. Yeah. Well, let's see. I mean, here for example, this one is V1. For example, this one is V2. For example. So and so you really don't need to. Yes. Yes, so there's a, well, you can apply check for permutation, etc., and go to R check, but it's yes. But I think this itself is R, I guess. But yes. Hopefully things are clear. Oh, what about notation? Sorry, I'm a little bit sloppy with notation right now. So any other questions? Yeah. Okay, if not, let me then evaluate this diagram and then show that it's a classical. Okay, and that itself works for any, okay, not after any, but for variety of spectral curves. And depending on which spectral curve you choose, you get trigonometric or elliptic algebras. And but let me do the case of the Yangian because it's the simplest case. Otherwise, we run into zeta functions and things like that. So. Okay, so let's see. So the final diagram. Okay, so let me write on the same diagram again. And the story is somewhat similar. So here we write on X and Y. That's the same notation as Brian. And then there is also a Z direction. These are located points, Z1, Z2. And then the structure is similar. First of all, we have the integral over X and Y, just as in the leaky number case. And then there is a gxy. Okay, so here it's a point x, z, 0, z1. So this is like a 0, y, z2. So because here I'm just parametering the points, and the propagator depends only on the difference. So I have this x minus 0, 0 minus y, z1 minus z2. So, and I have to integrate it. And then this, okay, so what is this propagator? So propagator is again propagator 2 form. And it now satisfies this equation that this is equal to the distribution, but now in 4 dimensions. And then I also have plus gauge fixing conditions. Which I don't write down, but you can choose whatever gauge you want. Gauge fixing condition, just like in the before. And okay, so this is the inverse of this combination. And this combination appears because the action of the 4D Chern-Simons itself, okay, I'm standing here again. The action of the 4D Chern-Simons itself takes the form of A wedge dA, wedge dz. So, okay, I can bring it here, of course, and it's, there is a dz wedge d operator here, and then I've just taken the inverse of that. So that's the definition of G, and if you write, there is a formula for that. I think it's 2 pi or 4 pi, I guess, and x squared plus y squared plus zz bar squared, and there's a squared, and okay, probably the formula doesn't matter, but the point is that it exists. Y dx zz bar dx, and if I remember correctly, there's a factor of 2 or something here. So there is some similar propagator 2 form, which you can write down, and you integrate that. And well, except that of course here there is a gauge group dependency is not yet manifest, and that comes in because for each because here you have to choose a representation v1, v2, and so what you get in addition is that okay, so for first you have the here you have A and another index A. So you have TA acting on this weight space of this representation. Oh, okay, and then another TA acting on this weight space of another representation. That's what it means that this Wilson line is in this representation. So this one emits, and that's represented by these matrices. And yeah, so we have a tensor product of 2 operators, and then we have to sum over this index A, and so that gives the Casimir operator. So in the tensor product. And then this complicated integral, it actually simplifies. And sorry, I'm getting a mess, but then end result is that I'm going to get this first of all TA d1 times TA d2. So this is the Casimir operator. And then there is an expression like a z1 minus z2. And if you count the power of h bar, there is actually h bar is sitting in front. So this is the classical R matrix for the rational R matrix. So this is the classical R matrix for rational case. So, well, of course, in this case, the structure itself is a little bit trivial because it's essentially determined by the symmetry, etc. So, the answer itself is a little bit surprising, and you can even do dimensional analysis, and yeah, this is more or less the expected answer. But the point is not that we are reproducing this answer itself, but we have some constructive argument of how to compute this expression in principle, and then we can do other spectral curves. I think I'm running out of time, but for example, you can take well, okay, maybe there are a couple of interesting aspects. For example, you can do general, for example, elliptic curve and elliptic integral models. And people that certainly know that in general, the solution to the ordinary Yang-Baxter equation doesn't exist. You have to go to this dynamical Yang-Baxter equation. And there's a counterpart of that, in the 4D Chern-Simons theory, if you want to, okay, so if you analyze the classical equation of motion, then there is a holomorphic bundle on the elliptic curve, which in general is not isolated. So there is in general moduli. And so there is a moduli, and that should be incorporated. There is extra dependence on that parameter whenever you do this computation. And that parameter plays the role of the dynamical parameter in the dynamical Yang-Baxter equation, for example. So there is an explanation of the why you get the dynamical Yang-Baxter equation, and also why only for PGLN in that case, why there is a usual solution to dynamic. When only for that case there is no dynamical parameter. So that's the type of things. And but although some of the details of how things work out are not much then. So yeah, if anybody has expertise in elliptic cases, etc., I'd be happy to learn more. And maybe another thing is that I'm tempted to say is that there was already a discussion of 5D Chern-Simons, for example. So So this itself is the spectral variable parameter is just one, but there you can go to so-called 5D Chern-Simons, and in that case, in addition to the h bar parameter, you can turn on non-commutativity parameter. So that gives you more parameter, and then you get something like affine Yangian. And so it's an interesting question. And yeah, I think for example, G1 and others, Yehao and others worked on that, and also yeah, of course, by Kevin. And so that's reproducing the 5D Chern-Simons case is one advantage in this approach so far, at least compared to some other approaches. And the last thing I'm tempted to say is that okay, affine Yangian itself is a very interesting algebra, but somehow I'm recently working on some vast generalization of affine Yangian. I call it a quiver Yangian because it's associated with the quiver and Yangian. So it's if you're the type of person who are interested in cluster algebras and quiver representation theory, it's actually a natural thing. So but the difference thing is that input is not just the quiver, but the quiver with relations. So quiver with relations, people call it the superpotential. So if you have a quiver with relations, in my case, which comes from the toric Calabi 3, if it's the, in other words, the module category of that quiver with relation is derived equivalent to the coherent sweeps of the toric Calabi 3. If you start with such a pair, you can write down interesting infinite dimensional algebras. And that we call the quiver Yangian. And that contains the affine Yangian as a very special case. And then there is a statement, okay, that is self the definition of the algebra, but there is a statement that that it asks, you can discuss the representation soon, and that the representation is a fixed point on the moduli space of the associated quiver theory. So that's the type of the story, which also geometric aspect of the story. And so I'm now thinking about how all these discussions can be kind of incorporated. So that's the end of my remarks. Thank you.
Okay. We have 12 minutes before lunch. So any quick questions?
Indeed, lunch is supposed to be sacred, right? So
I know.
we should.
But
we still have a few minutes. Yeah.
Okay, I could ask.
Sure. Yes.
No, sorry, it's just like to understand the logic of it. So you have, I mean, you're saying that if you have the first order,
yes,
or the classical R matrix,
yes,
then if you like, then you know uniquely what the R matrix.
yeah, but of course that requires a proof. Yes.
But if, like, yeah, so you're sort of assuming that you will get an R matrix by computing. Yeah, it could also go the other way, right?
Yeah, that's right. So if you want to complete this argument, you need to prove the uniqueness argument. And so, for example, in fact, in order to make that statement, you have to make a statement a little bit more precise. Because, for example, if you have the R matrix, you can multiply by H bar dependent identity. Sorry, the 1 by 1 matrix, for example, like a factor. And of course, there is an ambiguity, right? So if you have the R matrix, so as long as the function satisfies some property. So there are, first of all, ambiguities in the if you just impose the Yang-Bak's equation itself, there are a lot of ambiguity. So the statement should be modulo that ambiguity. There is a unique answer, for example. And so there are various different ways of fixing that. For example, you can impose the entirety relations, etc. So you need a little bit more, relations. And then the statement, okay, under this asterisk, the statement is that if there is a solution to the Yang-Bak's equation, we start with some identity plus non-classical, first order piece plus some leading collection, but only check the first leading piece, and then all the other pieces are determined uniquely. And but the basic, at least the basic idea is that if you just write down the Yang-Bak's equation and expand, and then you can really solve it order by order. So at least that's the basic repetition, and just make it to proof, yes. And it's a little bit subtle. Okay, rational case is relatively simple, and I forgot which case. In part 2 of the paper, we have some more comments along those lines, but I forgot which case we covered in the end, like elliptic case, etc. You have to mess with the elliptic functions, etc. So I forgot which case we gave a proof or something like that. So yes, but that requires analysis.
So for here though, like this is kind of related, I think, like V1 and V2 to begin with are just representations of G.
Yes.
And then you.
Oh, okay. Yeah. Yes.
And then you're looking also, so that's kind of related. Yeah, you always have the class.
Yes.
You're looking at what representations actually quantize.
Yeah. That's right. So that's indeed an aspect which is not covered. In fact, it looks like like any representation of the G, and then it goes. But of course, that's not the truth. For example, and so there should be obstruction somehow.
Yes.
And there's an explanation of that. That's related with the. So in other words, so one way to say that, the physical understanding is that, okay, for take any representation of the G. not the Yangian, but the final dimensional part. And then, okay, then there is some object called the Wilson line. It looks fine. And then if there is such object, we should be able to compute this. And whatever the answer is, there should be a corresponding R matrix. But we know that it's not the case. And the obstruction is that in general, there are some interesting anomalies, what we call. So we make there is a gauge invariance and we want the things to be gauge invariance, but the gauge invariance is sometimes broken. And that anomaly is captured typically by the cohomology in this cochain complex, etc. So we have to show that, in fact, in order for the theory to be well defined, we have to, for the Wilson line to be well defined, we have to show that these anomalies do not exist. And in fact, so that's related actually to how we reproduce the full set of Yangian relations. So there's a most complicated set of Yangian relations, and like a Jacobi identity for level 1 generators. And then that one has a term and extra term, and that extra term can be related with the existence of anomaly. In fact, it was related to some two-loop anomaly, and so it was a complicated computation, but we managed to do that. So the short answer is that if you take account of all these quantum corrections and existence or absence of anomalies, then that is the most crucial ingredient for reproducing the interesting Yangian representation theory. Yes.
Asking simply, if I just used your recipe with arbitrary V1, V2 for representations of G,
yes,
where will it break down? You know it will break down at some point.
Yes.
If those representations don't lift to representations of Yangian.
Yeah. So okay, as far as this computation is concerned, it goes through. In a sense, I did the computation.
Yes.
Yes. Yeah. So in fact, how exactly does the argument go? Yeah. So in fact, that's somewhat related. For example, well, there is so baby version of that, which is that, for example, before coming to that, for example, why did we even use the fact that it's a real algebra, things like that? And then that comes in because we have some diagram like this, and AB, etc. So there are diagrams, and then there are several different competing diagrams like this, or there is a cubic diagrams, etc. So it's like some two photons comes in from outside, etc. And there are three different diagrams. And if you have these diagrams, and if you do the gauge transformation to one of them, it's actually in general not invariant. And it's invariant only when you impose the relation that the commutator of this is equal to that. So that's similar to this IHX or STU relation in the core diagram, etc. That is the classical argument why it should be a real algebra. Now, so this is a classical piece, but you can go to the one loop, two loop for this similar argument. And then there is a similar argument that's actually in the two loop order. You have to discuss more complicated diagram, something like this. So it's a two loop order. You have to discuss some diagram like this. There are two loops, so it's called a two loop. And so it's h bar squared term. And then, so there is a gauge field along, and then you apply the gauge transformation to one of these things, for example. And then the answer should be invariant, for the gauge invariance. And then in general, that's not going to be the case. And so that's actually, so that is the obstruction for defining this, lifting the representation of the final dimension piece to that of the Yangian. Okay. And so that is indeed, in fact, that is the most crucial part, the very most crucial part of the part one of paper, and that involves the two-loop computation. And that was, in fact, there are like 10 diagrams or so, and we have cohomological argument where only one remains, and then that I had to spend like 2 months to evaluate the stupid two-loop diagrams. And because I don't know, the computation itself is easy, but I was getting a factor of 5. I was expecting 2, but 5 is 4 plus 1, and I was so I really suffered with the factor of 2 and 5. But in the end, surprisingly, it works, even including the coefficient itself. So coefficient is sacred here, of course. So yeah, so that gives you a sense that Chern-Simons knows about. It's just that I'm not good at the computations and I could get them once, but Chern-Simons already knows. It's built in.
Is there a question?
Yeah, there's a question also.
Oh, sorry, yes.
What does it say?
Outside A, type A only said, oh, okay, yeah, I think it's related to similar question. Indeed, like for example, a joint of SOA. Yeah, so the question is that outside type A only side of certain ellipse of G can be lifted to representation Yangian. Yes, indeed, that's exactly the same question as Curtis was asking, and that happens, for example, when you have the, for example, like the favorite one is like a 248 of E8. In fact, Professor Chari and others have worked that out, and you have to add the trivial representation to make it to represent the Yangian. So there are obstructions, and you see that from the diagram argument too.
Okay, sorry, we have to go for lunch now. Let's thank Masahito again. So afternoon session start at 4, right?
Yeah.